Okay, we're going to talk about 7.5 logistical growth. But before we do so, we're going to start with the ideas of partial fraction, right? So in this case here, you see that you have a fraction, and this is the original problem here. You know that this fraction is made up of two separate fractions, and you're really trying to figure out what it was to begin with. Now, this is actually a very cool concept because think about what this is saying. That if you were looking at it as a number, right? 7, what plus what gives you 7? You have infinitely many possibilities. You could have 2 plus 5, you can have 3 plus 4. If you add in the decimals and the negatives, you have infinitely possibilities of combinations to make the 7. But what we're saying here is that to get this fraction here, there's actually only one combination that will get you that. And we're going to show you how to do that, how to find that combination, right? So if you look at the left-hand side here, you can break down the denominator and look at what you have to begin with. So it is x minus 12 times x minus 4, like so. So I'm saying that sum a over x plus sum b over x minus 4. Again, these came about from the factors of the final answer. And so what were the numerators of those smaller fractions to add up to this fraction of x minus 12 over x squared minus 4x to begin with, right? So remember, all along the semester, I've been doing this crisscross applesauce and adding out fractions. This is where it actually gets really handy. So you have x minus 12 over x times x minus 4. On the right-hand side, you can do your crisscross, right? So a times x minus 4. And then here, this is your cross, b times x, right? B times x. And here's your applesauce on the bottom, x times x minus 4. Now that my denominator matches perfectly, you only need to deal with the top. So you're really looking at your equation as x minus 12 equals ax minus 4a plus bx. So this is where it gets a little bit tricky because we have so many variables here. You really want to look at, the focus is looking at the a and the b. All right, so the x allows you to kind of group your variables together. So what am I saying? Here's your x. Here you have one x, right? Here's a variable that has, here's a term that has the x. Here's a term that has the x, and here's a term that has the x. So if I were to group them together on the right-hand side to show my work, I see that 1x is equal to ax plus bx. If I were to factor out the x completely and kind of get rid of it, because that's really not my point, you will see that 1 equals a plus b. Okay? Now let's look at the other part that's left. I have negative 12 equals negative 4a. These are the terms that don't have the x's. So negative 12 equals negative 4a. Well, this is nice because I only have one variable, so I'm able to solve. I'm able to say that a equals 3. Now that I have a equals 3, I can go back and solve for b because I know that a plus b must equal to 1. So 1 equals 3 plus b must equal negative 2. So what that allows me to do is allows me to figure out what this fraction is. So x minus 12 over x squared minus 4x, this fraction can be broken down into 3 over x plus negative 2 over x minus 4, right? So that's the only combination. There's no other combination that would get me that final answer of x minus 12. Now, what if you swap it? If you swap the x minus 4 and the x, that's totally okay because your numerator will actually swap with you, so you don't have to worry about which order to have it in. So what's the point of all this? The point of all this is so you can take the integral like we do in number 2 here. When you have the top degree lower than the bottom degree, you have to do this partial fraction where you split it up into 2 smaller, simpler fractions so you can actually take the integral. If the top degree is higher than the bottom degree, you can do long division and clean it up. But vice versa, when the top is smaller than the bottom, you have to do partial fraction. So that's what we're going to do now. We're going to take this and go, okay, first of all, I'm going to look at this and say, this 2x plus 16, if I factor the bottom, the denominator factors into x plus 3 and x minus 2. That means my original fraction was something over x plus 3 and then something over x minus 2. Again, if you swap the x plus 3 and x minus 2, like if you did x minus 2 first and then x plus 3, that's totally okay. Your numerator would just kind of swap at the same time. So we're going to do the same thing we did with number 1, where we're going to crisscross applesauce, and you'll see that your denominator actually cancels out beautifully. So you're only dealing with 2x plus 16 equals a times x minus 2 plus b times x plus 3. Okay, all right. So now I'm going to go ahead and distribute this out and get 2x plus 16 equals ax minus 2a plus bx plus 3b. Okay, same as before. I'm going to use the x to kind of group my variables, right? So I have 2x ax and bx. So 2x equals ax plus bx. And again, now I don't really need the x anymore. So 2 is really equal to a plus b. All right. If you want to know, what I did was I really factored out the x and then put a plus b here. So that way I can see that 2 is equal to that because x is equal to x. That's what I'm really doing. Okay. All right. So now I'm going to look at the remainder, the constants. Here I have 16 and I have negative 2a and I have plus 3b. So 16 equals negative 2a plus 3b. So now I want you to focus on this. I want you to focus on the fact that, hey, now I have 2 equations and 2 unknowns. My goal is to solve for the a and b, not the x. X was just there to help me group my variables and group them into the right equation here, right? So this is a trip down memory lane. You got to remember, this is what you did in Algebra 1. We did elimination. You have 2 equations, 2 unknowns. You could do substitution, you could do elimination. For me, personal preference, I like elimination. So what I could do is I could take this equation as is, and then I can multiply this equation by 2 on both sides to get 4 equals 2a plus 2b. Right? Remember, you could do that. You can multiply both of them by the same thing so that it is balancing your equation. And then elimination says, hey, add these up. You will get 20. This is why it's called elimination, because this gets eliminated. And you're left with 5b. So b equals 4. Beautiful. Once I have b, I can plug it into any of the equation. I can plug it into the first one or the second one. I'm just going to go with the first one. So 2 equals a plus 4. So a equals negative 2. All right. So now my partial fraction gets split into negative 2 and 4. So this integral now becomes negative 2 over x plus 3 plus 4 over x minus 4 dx, right? And actually you did the hard part. This is now the easy part. We're now going to take this and now take the antiderivative. Remember, this is an x to the 1 power down here, an x to 1 power. So when you're taking the integral of x to 1 power, it becomes natural log, whether you have a constant with it or not. The top is your coefficient. The coefficient stays. So when you take the antiderivative, it becomes negative 2, natural log of x plus 3. Make sure to put absolute value around it because you can't take natural log of negative numbers. And then 4 is your coefficient of the next term, natural log of x minus 4. And since there's just an indefinite integral, there's no interval here, plus c. And that's your final answer. Now, I didn't guarantee it's going to be prettier, but I guarantee it's workable. So this is definitely workable, okay? All right, we're going to switch gears real quick, and we're going to look at this. Just to make sure I have the same thing, I should have this, right? So when we talked about in 7.4, when we talked about exponential functions, we were talking about growing bacteria in a dish, or, talking about a population of a town or a population of animals. But you got to keep in mind that all these population growth, yes, it follows the rule of exponential growth, which was the y equals y naught e to the kt, or what I said in the video, I say you could actually use a perp because it is exactly the same thing. But keep in mind that when you do that, you are assuming that you have unlimited food and unlimited resources and unlimited space to do this. It's not the case in reality, right? So there's something called a carrying capacity, because your food and your resources in your space is limited. At a certain point, your population will be hindered and you have to stop at a certain point. So for exponential growth like this, it starts slow and it goes up really quickly. It grows exponentially, right? But because of this carrying capacity, my new equation is going to look like something like this, where it grows exponentially, but it plateaus out. It eventually plateaus out because that's how much the space can hold. It can't go any more than that. So your goal is to really figure out what is the carrying capacity, right? What can I do to not get to that point? Because that is the maximum you can be, okay? All right, so we have a couple of equations here. The first equation here says, all right, dp dt, the rate at which this population is growing, is modeled by this example, this equation of kp times m minus p. Now, side note, rest assured this will be given to you on the test or quiz if you are to use this equation, okay? All right, so keep that in mind. I'm gonna look at the first thing it gives me. I'm gonna match this to what I saw down there. This is kp times m minus p, which means k is 0.0008 and m is 700. All right, k is the rate at which this is happening. It's 0.08% because you gotta move the decimal 2 places, and my carrying capacity is 700. So that answers the first question. What is the carrying capacity of the population? So the carrying capacity is 700. Okay, now it says, what is the size of the population when it is growing the fastest? So what is P when it's growing the fastest? So if you look at the equation here, remember how my growth starts exponential, it starts slow and it grows exponentially fast and it plateaus. So where is my growth the fastest? What's where the slope is the steepest? And it's right here in the middle of my graph, because that's where my slope is the steepest. And that is exactly halfway of your carrying capacity. So this is half. And it's right here. See, growth rate is maximized when the population reaches half the carrying capacity. All right, so we come back up here. So what is half of the carrying capacity at 350? So it's growing the fastest when population is 350. And again, I don't know what 350 bunnies, 350 horses, I don't know, but this is population. Okay. All right, part C. Find the rate at which a population is growing when it is growing the fastest. So here's a key word. We're looking for the rate. What is the rate? Rate is derivative. Oh, there's derivative right there. So what that tells me is I'm going to go ahead and plug in the fastest. I'm going to plug in the population when it's fastest into this equation P, so then I can figure out what the rate is, right? So you're going to go ahead and use this equation because that's the rate at which this is happening. 0.0008 times 350, because that's your population right now. And then 700 minus 350 is another 350. So yes, you need to use a calculator for this and punch it all in. So I'm going to really quickly grab my calculator and see 0.0008. Don't forget to keep your decimals, all right? Keep your zeros. So you get 98. 98 what? 98, again, horses, bunnies, whatever, per year. If they don't tell me the time, you can assume it's year. Year is kind of like a flat assumption you can make, unless they tell you in the problem, oh, this is going by week, going by days, going by whatever, then you got to change your unit of time measure, okay? All right, the next piece is a little bit more algebra heavy, so make sure you follow along and pause if you need to, okay? So solve the initial value problem using partial fractions. So remember to remind myself, when it says solve the initial value problem, I'm really solving for the equation. I'm going for y equals. But since it's a dp dt equation, really what it's looking for is, I want this equation. How are you going to rewrite this and solve for this equation? Okay. All right. So I see that I have a derivative here, which means I have to separate my variables and do separation of variables to take the integral and get my original equation this way. So since you have p on this side and you see p here and p here, that means all these variables are going to stick to the left, and you can actually keep your 0.00008 on the right hand side, because that one doesn't have to go with a p. So you go dp over and divide the p and the 700 minus p over, keep the 0.008 dt on this side. Okay. All right, so we know how to solve for these, right? We just take the integral, because that's how we get rid of the dp and the dt. Now, if you take a look at the left-hand side, you'll notice that this is not as doable as we want it to be, because you have two p's in the denominator, and the only time I can take the antiderivative is when there's one single p in the denominator, right? So this is where we have to use the partial fraction that we did previously in numbers 1 and 2. Okay, so we're going to use partial fraction to help us solve for this integral, right? So off to the side, I'm going to work on this and say, okay, I have this fraction here. This is 1 over p times 700 minus p. What was it before? What was it for a over p plus b over 700 minus p, right? And again, I got the 1 because there's an invisible 1 here, right? There's 1 times dp over there. Okay, and this is already factored for me, so I don't need to work on the factoring like I did in number 2. Okay, so I'm gonna go ahead and crisscross, right? A times 700 minus p plus b times p. So I get 700a minus ap plus bp, right? So again, I'm solving for a and b. So the p is kind of like the x I had in the previous problems. So that's weird. I have a p term here, I have a p term here, I got nothing over there because there's really a 0p here, right? So I can go ahead and set it up and say 0p equals negative ap plus bp, right? So that's really saying 0 is equal to negative a plus b. You can add the a over, a equals b. That's great, because now I can work on the other piece, the constant piece. So I get 1 equals 700a. So a is 1 over 700. And since a is equal to b, this is also what b is, right? So now I can replace that as my integral. So over here on the left-hand side, this now becomes integral of 1 over 700 over p, it's this first fraction here, plus 1 over 700 over 700 minus p, so the second fraction, dp equals integral 0.0008 dt. Okay, now I know this is very ugly. This is all very not clean. So let's clean this up a little bit. That 1 over 700 is bothering me a little bit. So I'm going to multiply both sides by 700 so I can get rid of the fraction. I can't get rid of the p because that's a variable, but I can multiply by any number so I can balance the equation and make my equation a little bit easier and doable. So this becomes integral of 1 over p plus 1 over 700 minus p dp. And then if you multiply that out, I get 0.56 dt. Okay, now I'm ready. You have 1 over p. Remember, that's like 1 over x. The variable is to the 1 power on the bottom. So this becomes natural log. So natural log of p plus natural log of 700 minus p, right? But don't forget, because it's a minus p, that p has a derivative of a negative 1. So it needs to come outside and become negative here. That's a chain rule there, okay? And then you take the antiderivative here, that's just negative 0.56 t plus c. Okay. Now, don't forget there's an initial value here. It tells you when p equals 10, when t equals 0, p equals 10. So it wants you to plug in 0 and 10 for your p and t respectively. So 10 is here, and 0 is here. Okay, so that means natural log of 10 minus natural log of 700 minus 10 equals 0.56 times 0 plus c. Okay, so clean this up. Natural log of 10 minus natural log of 690 equals c, because 0.56 times 0 is 0. So if you recall, we did a quick review on the laws of log and natural log. So you can combine the left-hand side into natural log of 10 over 690, which is really natural log of 1 over 69. Okay. All right, don't put it in the calculator. You actually want to keep it like that. So now I'm going to plug that in back into my equation here because I've solved for c. And remember, we're going to rewrite our equation, right? So natural log of p minus natural log of 700 minus p equals 0.56 t plus natural log of 1 over 69. Now notice I put parentheses instead of absolute value because I know that 700 is my carrying capacity. So it means whatever population I have is going to be less than 700. So I have no worries that my natural log is going to be negative in the parentheses because 700 minus any number smaller than 700 is going to be positive. Okay, so we're going to do the same thing as before. We're going to combine left-hand side into one natural log because then I can actually work with it. If you still want to know, if you want a reminder of where we're going, we're trying to get it to this equation here, trying to get p, one single p on the left-hand side, okay? All right, so then you have natural log of p over 700 minus p equals 0.56 t plus natural log of 1 over 69. Okay, now that I have a single natural log, the way to get rid of it is to take e to both sides, e to this power, e to this power, right? So what that does for me is then it brings this down, the e and the natural log reduces that, brings that down as p over 700 minus p. And then this makes it so it's e to 0.56 t. That plus allows me to say e to the natural log of 1 over 69, right? Because the plus says that I am actually just multiplying together the same basis with different exponents. So you have p over 700 minus p, e to 0.56 t, and this reduces out same as before and brings it as 1 over 69 like so. Okay, the rest is algebra, so it's going to be a little bit tricky, but it's not impossible. So you have p over 700 minus p. If I combine these 0.56 t over 69, I now have two fractions. I have fractions on the left and fraction on the right. I can actually go ahead and reciprocal both of these so that I make it to what I want. This is a little bit of manipulation. You have 700 minus p over p equals 69 over e to 0.56 t. That way I can see that it's really 700 over P and then minus P over P, which is minus 1. So 700 over P minus 1. Why do we need a 1? Look again, look over here. You see how there's a 1 here? I need the 1 somewhere, okay? And then on the right-hand side, I'm gonna write it as 69 e to the negative 0.56t. That way I can move it up so it's not a fraction anymore, right? All right, so you're solving for P, we're almost there. We have a single P now. Add the 1 over it, so 700 over P equals 1 plus 69 e to negative 5.56t, right? And so if you wanna put this over 1, actually multiply both sides by P because you're trying to solve for P. So 700 equals 1 plus 69 e to negative 0.56t times P. So last but not least, P is equal to 700 over 1 plus 69 e to negative 0.56t. And that is my equation, okay? Walk this through a few times, try to make sure you can see all the steps and understand how to get from my derivative of dp over dt all the way down to this final equation of P equals your carrying capacity on top and the rest of the terms, okay? All right, that's it.